Hello and welcome to this video lesson. Today we will be looking at the concepts of parallel circuits. In a parallel circuit, the electrons or charges have multiple paths to flow. So for example, in this one, as electrons start moving, once they get to this point, they're either pushed, so you remember there's a force pushing them, they're either forced through this resistor or this path or this path, and they have to come back all the way to the battery and move, and next time they might go through this one, next time they might go through this one, but the idea is that they have multiple paths to flow. The location at which their path changes or location where three or more wires meet is called either a junction or a node. So in this case, this is one junction here where as electrons are going, there's one wire here, one wire here, one wire here in order to make this connection. And in here, we got one wires, two wires, and three wires. So we got total of three wires in this junction and three wires in this one. The advantage of this is that if one of the bulbs burns, so let's say these two are light bulbs, and let's say this one burns, so electrons are moving here. If this one burns, it means that these electrons can no longer move. Their path closes. So as these electrons are coming, they can no longer be pushed in that direction. Instead, they will go here. So everything in your houses are typically connected in parallel. And every time you plug something, it will be connected in parallel, because if it wasn't, and if it was connected in series, if one of them breaks, everything stops working. Whereas in these ones, if this one stops working, or if you turn this one off, it doesn't affect other components. The disadvantage of the parallel circuits, and I didn't write that one down here, is that if one of these short circuits, it means that all the current will start going through that path because there's no resistance there. So there's some resistance here, no resistance here. So when the electrons are being pushed and there's resistance here but no resistance here, all of them will end up moving here. That speed of those electrons will increase, current increases, heats up, and it could damage the different parts of the circuit. That's why typically we use different components in order to help to avoid that. So for example, we can put a fuse, which is a very thin wire that if the current goes too high, it just burns and it just causes a open circuit here, so it doesn't damage the source or other components. Or we use a circuit breaker in which it automatically switches off this specific path if the current goes too high. Let's talk about potential difference in parallel circuits. So in this specific case, we got charges moving through the battery, and not really moving through, but get recycled here, and electrons will start moving in this direction, and they will either be forced in this direction or this direction. And there's a little bit more traffic here, so most of them will probably go here. We'll talk about currents in a second. And if they go here, they will come here. Remember, there's some currents also coming from this direction. So, and the potential difference is from this side, the electric fields are going from negative side of the battery to the positive side. So there's no reason for them to try to go back, and there's too much pressure from other charges which are moving in this direction. So this charge is not going to go back in this direction. It's going to come down. It's going to go through the battery. So it can either go through this loop or it can go through this loop. It can't go through both at the same time. So when we're analyzing the potential difference, we either have to take loop A or loop B. Let's do both. In the first one, I'm going to take loop A. And I'm going to say this is for loop A. And let's say as it's going through the battery, it's going to gain certain amount of potential. In this case, I didn't really write what the EMF is. Let's imagine that the EMF is, let's say it's 12. So as it's going at position 1, it has no potential to bump into anything. At position 2, it now has potential to bump into things and transfer energy. So it has exactly 12 joules that every charge can spend. So it's going to come. Loop A is the one and down here. So it's going to go here. It's going to bump into this one and bump into this one, spend all its energy and go back here. So it's going to have 0 energy at position 4. Between 2 to 3, it didn't really lose any energy because it didn't bump into anything. So energy here for each charge is 12. And then between 3 to 4, there was a voltage drop because it transferred about 6 joules of energy to this particle and 6 joules of energy to this particle and was left with nothing at the end. So it's going to go to 0. And then from 4 to 1, it's not really bumping into anything, and it doesn't have any potential to bump into anything before it goes to the battery anyways. So it's got 0 potential there. So I can write the 0 here. Now for path B, the charge is going to go through position 1, it's going to go to 2, it's going to pass position 3, go to 5, and then go through this resistor instead and come back. So at position 1, it's got 0 potential to do any work. As it moves along to position 2, it gains electric potential of 12, so similar to last one. From 2 to 5, it doesn't actually lose any of that energy, so that energy is constant up to here, or the potential to do work is constant all the way to here, so that's still 12. From 5 to 6, it loses some energy here, some energy here, some energy here, some energy. It's got a total of 12. There's 4 obstacles, so it's losing 3 when it hits each. And it's left with 0 at the end. So the total energy at the end here is going to be 0. And from 6 to 1, its energy doesn't change. So here I'm going to put 0 all the way to here. Note that the potential did not change for both of them. It was exactly the same. And even if I added another path, the charge would gain 12 joules of energy and lose 12 joules of energy. It would always go to 12 and come back to 0. The idea is it doesn't matter where the resistor is. If it's in parallel and if it's only one resistor, it will always have 12 joules before it goes to the resistor and 0 afterwards. So the potential doesn't change. So the way we write that, and we did this in the past, we said in a loop, the total amount of energy that's gained, or the total amount of potential difference gained, is same as the amount that's lost. Since all the loops have one resistor and one battery, so every loop that we look at has one source and one load, that would mean that the potential difference of all the loads are the same as the battery or the source. So this is a therefore statement. So in a parallel circuit, the potential difference in all the components are going to be exactly the same. These are parallel circuits. These are not mixed circuits in which you have multiple resistors. These are the ones in which you only have one resistor for each path. And just to remind you, this idea of losing energy, gaining energy and losing energy is the idea of conservation of energy, which says that energy can neither be destroyed or created, it can only change form. So energy goes from chemical to electric potential, and from electric potential to kinetic, and from kinetic to kinetic particles of here, and then from kinetic particles of that to other forms. And that's the idea of here, where in a loop, the total amount of energy does not change. Now, current in a parallel circuit is an interesting one because when we got charges moving, we got the total amounts and the IT here refers to the current across a battery. We got this current going in. Some of it will go here and some of it will go here. So not all the charges are moving to the same one. The amount that moves to different ones depends on the total resistance of each one. Here we got more traffic on this path compared to this one. So current I1 will be quite larger than I2 here. So the total current here will be exactly actually twice as this much because there's twice as less obstacles to go through. So as the total current is coming in, some of it will go here, most of it will go here, and some of it will go in this path. At a junction, current changes. And the way we write that is that at every junction, the current that goes into the junction will equal to the current that's coming out of a junction. And let's do some calculation in this one just to show you how this is. So let's say the EMF here is 12. And let's say if it's 12 here, based on the last slide, we learned that the voltage here, V1, will also equal to 12, and the voltage here, V2, will also equal to 12 because charges will come in with 12 and lose 12. These charges that go through this path come with 12 and they lose 12. But the current across this one will equal to the potential difference here will equal to the current multiplied by the resistance. So in the current here, I'm just going to do the calculation. We'll do some examples a little bit later. Will be 12 divided by 2, which is 6 amps. And the current here, I2, will be 12 divided by 4, which is 3 amps. And as I said before, the total current, because we got more traffic here, it means that the current will, or the charges are moving slower in comparison to this one. The charges here will be moving at a speed twice as fast in comparison to these ones. So that's the idea of the current here, but the idea here is that whatever current goes into a junction is equal to the current going out. So we can write this in two different ways. For this junction over here, I'm going to draw it in red, and I'm going to call that junction 1. Current coming in, the one that goes into this junction is IT, and the one that goes out of it is I1 and I2. So I can write that IT, which is in, is equal to junction whatever goes out, which is I1 and I2. So IT here, I don't actually know what that is. I know what I1 is. It is 6. And I know what I2 is, which is 3. And that's total of 9 amps for this specific circuit. I can also do this the same way with the other junction, this one, and I should get the exact same value. So for junction 2, the current that goes into this junction in this case is I2 and I1. These are going into the junction and IT is coming out. So I1 plus I2, whatever goes in, will equal to whatever goes out, which is IT. And I know I calculated I1 to be 6, I2 to be 3, and that equals IT, and IT will equal to 9 amps, which is exactly the same. Now, this total current that goes, total current or IT is referring to the current that goes through the battery. And this is also called the IS sometimes, ISS standing for source. One interesting idea here is the way a lot of circuitry in your devices are generally hooked up is always in parallel. So let's say you got your phone, and let's say your phone has your speakers. Let's say it's got your screen. Let's say it's got your microphone and bunch of other components. And in this case, as soon as you change one of the resistances here, the total amount of current that goes through these components changes. So for example, if you're not using your speaker at all, then there's no current going through this one. Let's say you're watching some show and you're just watching it on silent. So the only current going through your circuit is here. So the total current will equal to the total current going through your screen. But then as you raise the volume, the total current here changes. So you're adding more and more current here. So now your battery needs to provide more current in order to be able to power up not just your screen, but your speaker as well. So by turning on more and more components, let's say you're doing a video call where you got a speaker, you got your screen, and you got your microphone all turned on at the same time, then you need to, your battery will provide more current or more charges every second in order to power everything up. And the more current that it is passing, the more charges that is passing, it means that it's recycling more electrons every second and is being used up faster. So that's why your battery dies faster when you turn on all your components. And that's why IT here, or I of the source, or the current of the battery, is actually increasing. As we mentioned in the past, the total resistance is the resistance experienced by a source as it pushes the electrons throughout the circuit. So it can be calculated in different ways, but one way is that it's the total EMF divided by the total current going through the battery. Now, as we said in the last slide, as we add more resistors into the circuit, the total current increases. It means that I need to power up more components, and that would mean that I need to have more current going through the battery. And resistance here felt by the source is actually going to decrease. What this is saying is, oh, the total resistance is the EMF. The battery power isn't, not the power, the potential difference isn't changing. It's able to recycle the same amounts of battery around this area. But as soon as I add more and more components, what I need to be able to do is I need to provide more, it needs to happen faster. So the recycling needs to happen faster so it can power more and more components every second. So as I do that, the current is increasing. And remember, idea of resistance is that it opposes the electrons, but within the battery, the electrons are moving faster and faster, or being recycled faster and faster, and that's actually reducing the total resistance of this. So as I add more and more resistors here, the resistance in different areas is changing, but the total resistance felt by the battery is actually decreasing because it needs to provide more current through. Now, the way we calculate this resistance mathematically is 1 over the total resistance will equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot dot dot. So that pattern continues and continues. I'm not going to go through the proof in this specific video, but I could make a separate video kind of explaining the mathematics of that. How we use this equation, though, I'll go over. So in this specific case, I have two different resistors. So I'm going to say 1 over the total resistance is equal to 1 over my resistance 1, which is 2 ohms, plus my 1 over resistance 2, which is 4 ohms. I'm going to take common denominator of 4, and I'm going to go 2, 1, and 1 over RT will equal to 3 over 4. And since 1 over RT is equal to 3 over 4, it means if I take the reciprocal of both, I get RT over 1 is 4 over 3. And if R over T is equal to, in this case, 1 over 3 repeated, and approximately to 2 significant digits, because all the other information are given to that, it's going to be 1 over 3 ohms. So this is the equation that we typically use to find the total, or what we call the equivalent resistance of all the resistors. And we can see that even though one resistance was 4 and one was 2, the total resistance actually ended up being less than both of them in this specific case. Let's do a few examples here. So on the very first one here, I got a battery connected to two resistors. I got the two resistances here. I can calculate the total resistance here. But let's see if there's an alternative way to do this a little bit faster. I have the potential difference here is 24. And remember, in a parallel circuit, as the charge gets a certain amount of energy here, it has to lose it all here. So in a parallel circuit, the EMF is equal to delta V1, which is equal to delta V2. This is because it is parallel. And you can also use loops to write this. And this one will mean that delta V1 will equal to delta V2, which is the EMF, which is, I could have just done it in one line. I don't know why I wrote the second one, but this is 24 and this is 24. If I were to write this using the idea of loops, I would write it as such just to show it to you. Let's say this is loop A. I'm just going to write it for loop A just for an example. Loop A, total amount of EMF is equal to the total amount of voltage. In loop A, we have EMF and delta V1, so whatever energy is gained here is lost in V1. And that would mean that 24 is equal to delta V1, and delta V1 is equal to 24 volts. So alternative way of writing the same thing. This is just enough. You don't really need to write that for this specific case. Once I have this set of information, I have enough to find the current here. I have enough to find the current here. So I'm going to write this as delta V1 is equal to I1 R1. 24 is equal to I1 times 2. I1 divide both sides by 2 and I get 12 amps. Delta V2 is equal to I2 R2. Delta V2 is 24. I2 I don't know. R2 is 4. Divide both sides by 4 and I get I2 is equal to 6. To find the current here, I'm going to take a specific junction. So let's take this junction over here. I'm going to call this junction 1. And I'm going to draw the direction of current. This is IT coming directly from the battery. This is current I1 going through resistor 1. And this is I2 going through resistor 2. So at junction 1, total amount of current going in is equal to the total current going out. Total going in here is IT. That's what's going into the junction. What's going out of the junction or exiting the junction is I1 and I2. So I'm going to add them together. And the symbol again, it just means sum or addition. So IT is what I'm trying to find, or the current going through the battery. I1 I calculate as 12, I2 as 6 for a total of 18 amps. So I'll write this down. And finally, I have two pieces of information here. I can find a third one. So I can go ahead and say the EMF is equal to IT times RT. EMF is 24. IT is 18. And this is RT, and RT is equal to divide both sides by 18 to get 1.3. And this is approximately 2 significant digits. I'm going to go with 1.3 ohms. And I think I forgot the .0 here. And that's it for this type. Now, alternatively, I could have used this two set of information to find RT. So if I wanted to use that method, I would have written this as 1 over RT is equal to 1 over R1 plus 1 over R2. 1 over RT is equal to 1 over 2 plus 1 over 4 is exactly the same question I did last time. Take a common denominator of 4 or do this in your calculator and take the reciprocal. That's also an alternative way of doing it. And you would get 3 over 4, 4 over 3. So this is 3 over 4. And RT will be the reciprocal of that, or the switching of 4 and 3 to get 4 over 3, which is approximately 1.3. And once you have that, you can find the rest of the information. This is also a good way to check your work because you use another method to finding RT as 1.3, but you can use this to confirm that your answer was correct. You can also do another check as well. 2 times 12, 24, 4 times 6, 24, 1.3 repeated multiplied by 18 is 24. We got a parallel circuit. All voltages are the same. Current going in is current going in is 18. 6 goes here, you're left with, 6 goes here, you're left with 12 going here. Let's try the second example. Again, from these questions, there might be multiple ways of doing it. I'm just going to go through one method for this one and see how it goes. In this one, I have two pieces of information here, so I'm going to go through this one a little quicker. I'm going to say delta V1 is equal to I1 R1. Delta V1 I1 has a value of 3. R2 is 2, total of 6. Once I have the voltages, I know that in a parallel circuit, delta V1 is equal to delta V2, which is equal to the EMF, which is equal to 6. We just calculated that. This is because it is parallel. It can't be a mixed circuit, so it can't be a mix of parallel and series for this to work, but these are all 6. Now I have two pieces of information here, so I can find the third one. So I know that delta V2 is equal to I2 R2. I know that this is 6. I2 is what I don't know. R is 6. Divide both sides by 6 to get 1.0 here. Take a junction. So the current is going in this direction as IT. Enters junction 1, goes I1 and I2 go out. So at junction 1, we got IT is equal to I1 plus I2. That is going to equal to I1 is 3, I2 is 1. That's 4 amps here. And I know that the EMF is equal to ITRT. EMF is 6. This is 4 RT. Divide by both sides by 4 to get 1.5 ohms here. So that's my final answer there. I can confirm that part of the answer by doing a total resistance equation. So I can do 1 over RT is equal to 1 over R1 plus 1 over R2. This is because it is in parallel. 1 over RT is equal to 1 over, we got 2 and 6. Take a common denominator of 6 here. We got 3 plus 1. 1 over RT. At the numerators, I get 4 over 6. Take the reciprocal, 4 over 6, switch the numbers to 6 over 4, which is equal to 1.5, and that confirms the 1.5 here. Last but not least, you can try this question. Obviously, pause, try it out, but I'll go through the solution. In this one, I don't have two pieces of information for anything, so I have to kind of solve it in a different way. I know that I have the two currents here, so I'm going to take a junction. I'll do this. I'll take this junction here. Current IT, I1 and I2. So at junction 1, IT, what's going in is equal to what's going out. IT, battery 6, I1 3, I2 is the missing one. I'll subtract both sides by 3 to get 3 amps here. Now I have two pieces of information. I can find the third one, so delta V2, so our potential difference across 2 will equal to I2R2, which is equal to 3 times 2, which is 6. Is a parallel circuit. That's nice. We got delta V1 equals delta V2, which is equal to the EMF, which is equal to 6. This is because it is a parallel circuit. Makes these ones 6. You have two pieces of missing information. You know that the EMF is equal to ITRT. So 6 is equal to 6RT. RT is equal to 1. And finally, delta V1 is equal to I1R1, which is 6 is equal to 3 times R1. Divide both sides by 3 to get 2. And you can do one final check to see if RT's kind of makes sense in this. You could have find RT and then use that to find other information as well. As totally a valid method. It's just my way, is just one way of doing this. Two resistances here, so I'm gonna go like this. I got 1 over 2 plus 1 over 2. Resistance 1 and 2 are both 2. That would mean 1 over RT is equal to 2 over 2. RT is equal to, take the reciprocal, which is 1.0. And that confirms that the solution is the same using both of the methods. I hope this video was helpful, and I hope that you keep learning and that you change the world in a positive way. Have a wonderful day.